This is the story of energy, humanity's single most important resource. Energy is the force that built our modern world, but it's often invisible to us, hidden in plain sight. Before modern energy, people had to walk miles to get water, carrying it by hand or on their head. With a modern energy system, we can move water with an electric pump, freeing up precious time. Once water is plentiful, we can grow abundant food. And with abundant food, there's extra time for education. Educated people have access to economic prosperity. Some can even operate a business and accumulate wealth. With money, more people move to cities where there's more to do. Cities need transportation to bring goods back and forth. And people are more likely to travel to see the world. All of these luxuries give us a quality of life worth protecting and even fighting wars over. As a society, we're making decisions about energy that will impact our planet for centuries. So we must understand it. And we can understand energy by looking at water. Water is key to all life as we know it. Our bodies need water to live. Food needs water to grow. Getting clean water has been our #1 priority for thousands of years, for ourselves and our fields. But water is heavy. It is hard to move. It is difficult to treat. And that's where energy comes in.
There are strong connections between water and energy. It takes a lot of energy to get water into our homes and into our lives in the way that we use and enjoy water. And that connection between water and energy is something we call the energy-water nexus.
We always need energy in order to make use of water, and vice versa. We always need water in order to produce electricity.
We don't always think about when we turn on our lights that we needed water at the thermo power plants to cool the power plant, and so we need water to be able to turn on our lights.
We use more water for the light bulbs and electrical outlets and switches in our homes than through the taps and shower heads and faucets.
We just can't focus on one resource, so there's a whole set of issues that has to be addressed. How we manage water systems in cities, how we integrate infrastructures in cities, how we manage waste streams.
Nothing is free. We need to manage all of it. And if we don't manage water, which we have not done well at, we're not only wasting the water, it has embedded energy in it.
The challenges that we face regarding freshwater supply is how to bridge between the increasing demand and water availability.
Unless we integrate our thinking, unless we think about water and energy and food and climate together, we're going to make the wrong decisions.
This is Power Trip, the story of energy.
In the ancient world, water was a key for settling. Being located in the Middle East, we are part of the desert belt. So, of course, everything depends on water. Even the Old Testament and the New Testament, the Bible, all deal with water issues. We call it the Green Arc, from Iraq of today, Mesopotamia, west to via Syria to Palestine. That was the beginning of the civilization in the region. Everything based around water.
In the old days, people lived where the water was. They didn't have the ability to move water great distances. So people needed the water, so they moved to where the water was just so they could thrive. And that's the way it was for millennia. Even at a cellular level, you need water for the functioning of the cells. And we need water for the movement of nutrients around a body. We need water for the growth of a plant. We need water for all life.
historically, moving from a hunter-gatherer society to a more stationary society, without energy, the big challenges are the right kind of water at the right time at the right place.
In the modern world, energy and water are connected. This is called the energy-water nexus. We use energy to move water through pipes, to lift it, and to clean it. And we use water to produce energy. Thousands of years ago, water was moved across vast distances by forces of gravity inside massive structures called aqueducts. Ancient engineers designed these aqueducts to bring pure water from its sources high in the mountains down into cities and towns. The Roman Empire asserted their power by creating lasting cultural landmarks and water infrastructure, some of which are still standing today. The Romans celebrated water. They treasured water and built beautiful structures to show it off. Roman water infrastructure was a symbol of their dominance. As they conquered a new territory, they would Romanize it by building waterworks to project their power.
The Romans experienced many challenges in developing, their kingdom here due to lack of water. However, using their knowledge, let's say engineering skills, they managed to overcome these difficulties.
What we're seeing here is an aqueduct that brings water by gravity to where the port is, where the people were, where the palace was. And that's the old way we'd move water, by gravity. We didn't have electricity to move the water uphill.
Some of the amazing things about the Roman aqueducts is that they're moving water from a long distance in a very low technology way, using gravity. And it's really quite the engineering feat.
At the height of the Roman Empire, a simple gravity-fed system of bringing water down through aqueducts provided people with not only all the water they needed for drinking, but all the water they needed for bathing and cooking and everything else they wanted to use it for. In fact, in the Roman cities, people had about the same amount of water, 400 liters per person per day, that we currently use in our modern cities. So in some ways, the Roman Empire was a high point of early civilization.
For thousands of years, water has been important. You could use an aqueduct to bring the water to the people, or use a power plant to desalt it and pump it uphill to where the people are. And here at this one spot, we see the nexus of antiquity and modernity all in one place. We also see the nexus of energy and water all in one place.
The magic of energy is captured in other ways. There's the myth of the unicorn. The unicorn has the magical horn. What was magical about the horn is that it could rid a stream of poison. The horn had magical capability to treat and clean water. Well, today we use energy to treat and clean water. So with energy, we can have the magic of a unicorn's horn.
If we look at our modern lives, we have water and energy at our disposal for that hot shower, for washing clothes, for clean drinking water, electrification of our lives. It's not so recent in our history that that wasn't a possibility.
If plentiful, water can help civilizations thrive. A lack of water can cause societies to collapse. Researchers studying caves in China concluded that multi-decade droughts may have led to the collapse of 3 major Chinese dynasties. Drought also might have caused the collapse of the Mayans and the Native Americans of the desert Southwest. Multi-decade droughts are a possibility today, which raises a question about which societal collapses might be looming. In the Middle East, where water resources are strained, unrest is common. The displacement of Syrian farmers caused by a drought led to a flood of refugees crossing into Europe that affected election outcomes in multiple countries. In that way, it could be said that drought is affecting the power structures of the world even today. After the collapse of the Roman Empire, the infrastructure crumbled. For centuries, the aqueducts were abandoned, plundered for their stones. People tried to live close to water. Water began to be used for mechanical power, grinding wheat, sharpening iron, or crushing grains.
The most important demographic trend over the last few hundred years is movement from rural areas to urban areas. It's the growth in importance and size of cities. Cities are now the economic powerhouses. They're the political powerhouses. That's where the people and the goods flow. And when you have a concentration of a lot of people in one place in a city, you have to manage the water, the wastewater, and the energy to run the city.
It wasn't until the Industrial Revolution and the economies of Western Europe started growing that we needed once again to have an imported water supply, because places like Paris and London suddenly had populations approaching the size of ancient Rome.
The River Thames has been absolutely crucial to London. The Thames has been the access into and out of London from the time it was founded till now, 2,000 years of history, liquid history. All of this, all of where we're walking is made ground. This is the old riverbed. They call this the Watergate because this was where the river met the land. And if you wanted to take a boat across the river, you came down to a gate, a water gate like this. It's the only one left in London. At the start of the 19th century, London was a city of about 1 million people. By the 1850s, it had gone up to about 2.5 million. And the rubbish and the excrement and the sewage that just flowed out of the city flowed directly into the Thames.
In the 1800s, as London grew as a city and more people came here, the water was so bad, it was safer to go to a tavern like this and drink gin or beer because it was cleaner.
Of course, we didn't know what bacteria were, but there was something in water that often made people sick. But beer didn't, and that's because the fermentation process of brewing beer kills those bacteria. So drinking beer was actually a safer thing than drinking water.
In some ironic sense, some of the earliest ships that came to North America, they came with not water on board, but with beer. And when they ran out of those treated beverages, they didn't know what to do because they didn't know that they could trust the pristine waters of North America that were incredibly pure and safe to drink, because that wasn't their experience. So they had to land and they had to ferment new beers, new fermented drinks in order to provide safe, what they thought were safe beverages, because they didn't trust the water.
By the early 1900s, it became commonplace for industry to dump their waste into America's waterways. Almost all of the collected wastewater in the United States was released as raw, untreated sewage straight into rivers and streams, causing a danger to public safety and health. To encourage action, informational films like this one were made, which presented electric-powered sewage treatment as the way to clean up America's waterways.
Almost invariably, man settled near to water. Being near water, his communities dumped their waste matter, their sewage, into the streams for easy disposal. The germs of waterborne diseases, typhoid fever, cholera, dysentery, and other intestinal infections thrive in polluted water.
A century earlier, cities around the world had been ravaged by deadly waves of disease caused by untreated wastewater. Cholera was one of the world's leading killers and used to be all too common.
It was the 1850s, and cholera was a constant problem in cities around the world.
Cholera is a waterborne disease that was transmitted from water contaminated with human waste.
Paris, London, Moscow, cholera crossed the Atlantic and hit New Orleans and went up the Mississippi River and literally out the Oregon Trail.
In London, the waste had been just dumped into the River Thames.
The relationship between cholera and water was new. The belief was that cholera and other diseases were spread by miasmas, smells in the air. And you could understand exactly why people believed that, because London absolutely stank. But there was a doctor, his name was Dr. John Snow, who had a different idea. When he mapped deaths in his area, he found that they were very closely correlated with a particular pump, the Broad Street pump. He had the parish pump locked up.
Dr. John Snow discovered that link and was ostracized, but was posthumously honored for discovering the link between cholera as a disease and waterborne transmission of disease.
And in 1858, the conditions were absolutely right for what became known as the Great Stink.
In the summer of 1858, hot weather heated up the untreated human waste and industrial runoff, which was piled up along the River Thames, and the stifling heat trapped the foul air. The smell was so noticeable that London had finally had enough. The government worked with a civil engineer named Joseph Bazalgette to design a series of sewers. Pumping stations powered by modern energy were built to lift the sewage from the river up into the pipes. And Bazalgette's plans included 3 embankments, which closed in the sewers containing the waste.
London constructed hundreds of miles of sewers to move waste from the city area.
Those intercepting sewers took all the sewage and fed it downstream, and from there into the pumping stations, and then right out into where the Thames is tidal, and then it flowed out.
They built wastewater collection systems, or new sewers. In celebration of that, they built a bunch of water fountains around the city that gave access to clean drinking water. So water fountains like this one were built starting in 1859. This is the first one in London. Up to 7,000 people per day use this. It's not working today because we don't need it. We have piped water to our homes and businesses. Water fountains like these were a symbol that the water problem had been solved for metropolitan London.
Water is also critical to public health. Many of us take clean water for granted today. Ancient engineers solved the problems by bringing pure water from the mountains using gravity. But as pollution increased, it took modern energy to make that water safe for us to drink.
The role of rivers in America has always been for commerce. We had rivers that just permeated way into the landscape compared to a lot of the other regions that the settlers were used to. When settlers first showed up to the U.S., they moved as close to rivers as they could because that was the cheapest way to get commodities into and out of the landscape. As soon as the settlers showed up, one of the first things that they did was they started to build grist mills.
So in the upper Midwest, it was common to have grain mills that would take grain from the field and grind it into flour.
Then they look at the river and they're saying, there's a really nice waterfall. If we can put a dam there, then farmers, they'll come to the dam, they'll come to the grist mill. And not only that, but just downstream of that mill, there's a whole bunch of boats that are ocean-going vessels. The earliest form of the economy in the U.S. was small grist mills that were just taking the local grain and turning it into flour. And that then became one of the primary exports as well. This power-producing location becomes this entire nexus of society.
The energy of flowing water was used to grind wheat into flour and corn into meal. Before this, humans required about 2 days of labor to grind a bushel of wheat into flour. Horses could do the same work in a few hours. But a typical 18th century water-powered grist mill could grind dozens of bushels of flour or cornmeal daily. Rivers were turned into powerhouses to drive a gradually modernizing economy and feed an expanding population. The energy of flowing water was harnessed to manufacture goods and food, and then to transport those products to customers.
The Mississippi River actually runs right straight through the heart of Minneapolis and has provided power for everything for a long time. We are at the very northernmost lock and dam. This area here was pretty much all built up because of the water power here. It allowed them first to have logging mills, then it powered the flour mills, and then hydroelectric.
It was really when they crossed the Appalachians and moved into the Mississippi Basin, there's no river like the Mississippi in Europe, and that was a completely different ballgame. It's just big.
Watch your step, please.
I'll see the power of the falls. You can see it.
You're right on top of it here.
Yeah, I feel it. You can see how much is flowing. So if I were a pioneer and I found this spot, I'd want to build a mill also.
Exactly.
Find a way to harness that water power.
You've got natural power right here.
Yeah.
And never ending, basically. Back when they first got here, it was mainly mills. And then as people realized the power of the river and what they could do with it, the city started growing. The reason this dam is so important to the city is having the dam here, the lock, and the power plant over there, the body of water above us is called a pool, upper pool. Minneapolis gets all their drinking water from that upper pool. If something were to happen here, Minneapolis would have to find a different water source.
In many parts of the United States, water was available only from wells, from streams. In rural areas, certainly not. You wouldn't have piped water, and you wouldn't have access to electric power for pumps.
Hydropower has existed for centuries. Hydropower itself is just turning a really big wheel and then using that mechanical action to turn something else large.
So water for mechanical power was an idea that's been around for hundreds of years. Later on, in the late 1800s, the idea of using water for electrical power also came to life. You can use flowing water to spin a turbine, which spins magnets, which generates electricity.
Hydropower was not a new concept, but when electricity came into play, the need to generate electricity and combine hydropower into hydroelectricity was a big advancement.
So hydroelectricity came along. It actually initially started in Wisconsin, was one of the first dams that we know about on the Fox River up in Wisconsin, where instead of producing mechanical energy, it was instead the turning of the wheel was used to produce electricity.
If you have a good river site, some of the cheapest electric power is by building big turbines and using the fall of water to produce electric power.
Welcome to the Water Lab. We have 4 water tables here with a chance to learn about water power in lots of different ways. You're an engineer, right, Michael?
Yes, I am.
Okay, we're asking you to be a water power engineer today.
Okay, I'll do my best.
Your goal is to divert the water in various ways to get all of the water wheels and turbines spinning at the same time. Keep all the Minneapolis mills going.
All right, I'll see if I can build a bigger reservoir to create more water up top. All right, so now we got the turbines sort of flowing over here, but then we lose some power over here. And then what are these for? Build another reservoir up top?
Uh-oh.
Oh, we just had a dam collapse. So one of the things about building dams is you can have a disaster when they collapse. Look, now these turned off because I broke the dam. Oh, I keep crashing my... Hey, all right, I got all 3 water wheels working, although the turbines aren't working. I still have a lot to go. Something like this could be mechanical power to grind grain or to spin spindles for textiles or to make hydroelectric power.
The development of hydroelectricity, the big thing that it transformed initially was it allowed us, instead of building a manufacturing facility around gears, instead we had wires. And that allowed us to build very efficient manufacturing facilities. So right off the bat, we gained an enormous amount of flexibility at the manufacturing scale.
One of the biggest, most important electric installations in the history of the world was at Niagara Falls in the 1890s. That meant that power around the Buffalo, Niagara Falls area was the cheapest in the world, and meant that many industries that rely heavily on cheap electric power established them right there at Niagara Falls. Electrochemical industries, aluminum production, other electricity-intensive industries.
So we built these dams in the early 19th century. They were powering a lot of this growing industry. Then you scale that up, and now we realize we can move electricity a long distance. We don't necessarily need to build manufacturing facilities right next to a river. Now we can actually move those farther and farther away from rivers themselves. And that then starts to open up the idea of an entire electric grid. The 1920s especially was an era of, we were just starting to go into a dam building frenzy. That was driven almost exclusively by the private sector. So the private sector was building a lot of dams in ideal places. They were marketing that at private sector rates, and there was this idea that maybe those rates were exorbitant and that they were taking advantage of the limited amount of competition. Tennessee Valley Authority came online as a way to provide some kind of a cross-check. What makes the TVA unusual is it does everything. So it produces hydropower, it produces electricity, distributes that electricity, and then it markets that electricity. The Tennessee Valley was the dirtiest, poorest place in America. We weren't sure whether or not we were getting gouged by private electric companies. And FDR wanted to build something big. And so you put all those things together, and the Tennessee Valley was basically an experiment for all three of those things. The experiment was, can we electrify an entire valley? Can we, society writ large, take a dirt poor area and give it electricity, and will that area actually come out of poverty simply by introducing electricity into that area?
Government entities and private companies built dams across North America, harnessing the power of water. Dams reduced the catastrophic impact of floods, made river transportation easier, and generated electrical power, lifting people out of poverty and transforming our society.
The build-out of dams in the United States had a massive effect on rural electrification. A lot of that also came from building out of electricity infrastructure with transmission and distribution lines. But what that meant for rural life, specifically for women, was that they were liberated from a lot of manual labor. Electrification meant all of that was replaced with an electric pump, an electric stove, eventually piped water to the home. It's amazing what electricity can do for liberating women from housework that is so labor-intensive.
And as women became liberated from their chores, from the tedious tasks that were requiring so much manual effort, they could do other things. They could join the workforce. They could accumulate wealth.
Employers find that women can do many jobs as well as men, some jobs better.
So we see the rise of modern forms of energy and additional freedoms going hand in hand.
Day and night, in peace and war, the dams work for the people. Power for the factories, power for new industry, power to run 1 million machines, running out aircraft, tractors, textiles, engines, shoes, fertilizer, aluminum. Cheap and abundant power to light the cities and villages.
When we look back on it, there's an enormous amount of industry that is still based in the Tennessee Valley, and that's a remnant of the fact that the TVA produces cheap electricity. So you not only have the bomb-making manufacturer of Oak Ridge National Lab, but now you have a lot of the automobile industry is actually based in the eastern part of the Tennessee Valley rather than in Detroit. And one of the draws to that is cheap electricity.
The constructing of dams was often done for reasons not involving electricity. They were typically constructed in the United States as flood control infrastructure, as a water supply infrastructure for an industry. In a lot of the large hydropower dams that we have in the United States, power is actually an afterthought.
Dams have always been symbols of power. The way that politicians retain power and consolidate power.
Politicians historically love dam projects because there's a lot of money involved. The construction is expensive, and a certain amount of the money flows around to other people involved. The contractors for particularly the Mansfield Dam, which holds back Lake Travis, Brown and Root, were big financial backers of Lyndon Johnson's campaigns. And so he had an interesting cycle. Johnson would secure federal money, basically federally guaranteed loans, to finance the construction. Brown and Root would get the contract. They would make a lot of money. Some of the money would go to Lyndon Johnson's campaign funds. Then how would the bonds be paid off to pay off the loans? Lyndon Johnson organized rural electrification, which would then purchase the power and pay off the loans. and also endear Lyndon Johnson to the people of Central Texas because he provided electric power. So it makes a very nice self-reinforcing cycle of people getting real benefits, and some of those benefits paying off for the politicians who would help to secure them. Who are the losers? Well, the people who lived in the area right behind the dam. They get flooded out. Most famous examples of that are actually in the Tennessee Valley.
Every time we build a dam, something gets flooded. In this particular area, the best farmland in the Tennessee Valley is in these bottomland valleys. All of those are gone.
Those lands are often from vulnerable populations, from rural populations that have made their lives on the land, and from native populations that have had lands stripped away from them that are now flooded by reservoirs.
There are also environmental costs. I think those have been more serious in some areas of the Northwest, where the building of the dams has cut into or even destroyed the salmon runs. There are trade-offs, and the question is whose ox is getting gored, who's losing and who's winning. Hydroelectric projects are some of the biggest civil engineering projects ever in the history of the world. In many instances, I think it is a net win, but I think there are people who pay the price too.
We're often focused on one particular goal, and other issues that arise are peripheral. They're on the outside of our goal. And so a lot of times the environment does suffer in response to industrialization.
Unless you lived in a place where the release of the sewage made it impossible to live in the city because of the stink, we continued to release untreated sewage into rivers. The Potomac is impossible to walk next to. The Great Lakes are dying. All of the great rivers of the United States and Western Europe are suddenly getting polluted.
The Cuyahoga River is sort of a classic example of that. In the 1960s, caught fire because the industrial wastes that we were dumping there were burning.
And it wasn't the first time the Cuyahoga River had caught on fire. It caught on fire many times before that.
Really, in the 1960s was when rivers stopped being an asset and started to become a liability. I mean, it's not just the burning Cuyahoga River in Ohio. I mean, the entire Merrimack Valley up in New England was a cesspool. In the Southwest, the rivers are going dry, and in the upper Midwest and in the Northeast, they were just vile, sewage-laden waterways. And in the Southeast, they were just laden with silt from all of the agriculture. And so they were just nasty. It wasn't fun to be in a river by the time you got into the 1960s and 70s.
It seems the environmental movement was a series of things that all started to stack up. So in the environmental community, these were big moments, and it was a big opportunity to take action.
I think people were really fed up that, yes, it's great to live in a booming economy, but at some point, rivers should be flowing. We should be able to have our kids wade in a river without fear that they're going to walk out with all kinds of viruses and diseases and things like that. And that was the roots of the Clean Water Act.
The Clean Water Act was vetoed by President Nixon. He thought it would cripple the economy. Fortunately, Nixon was wrong, and industry and municipalities led the way with new technologies to treat waste and to treat sanitary wastewater.
Starting in the early 1970s, we invested billions of dollars in building or upgrading sewage treatment plants and turned our rivers and lakes and estuaries from places that no one wanted to go to places where now was safe to visit and to fish and to swim.
Those two laws, the Clean Water Act and the Safe Drinking Water Act, are the foundational water quality laws of the United States, and they are a key to providing safe water and protecting our natural ecosystems today.
A couple of years later, then you have the Endangered Species Act, and so that basically set out to start protecting all of these species. And then you just have all of these other acts, the Clean Air Act, the National Environmental Policy Act, so all these other things fall about, all from about 1970 to 1973.
Rivers improved in quality and lakes improved in quality. Of course, there's more work to do. Not all of the waterways in the United States are swimmable and fishable, but we're making progress.
Water is connected to everything we care about. Production of food, production of goods and services, human health, ecosystem health. But all too often, especially in the 20th century, we didn't think about the way those issues are related, but they're intimately related.
Growing populations and climate change are pushing us to a point where we can't get by with imported water anymore. And so if we need to find more water, we have to get creative.
Water is a critical resource for the production of the energy that we use. We use a tremendous amount of energy, and in the 21st century, if we're going to manage our resources in a sustainable fashion, we have to manage those resources together as a whole rather than as separate, isolated resources.
Economic development pollutes. I mean, that's just kind of a reality of just about any economic development. I think it's a degree of trade-off. How much pollution or how much environmental degradation are we willing to take for the benefits that it conveys?
One of the reasons why we're thinking more and more about the energy-water nexus is because we're reaching what I call peak water limits. We're actually finally running out of renewable and non-renewable water resources. And because of these limits, we're increasingly aware of challenges to our modern water system.
So we've found ways to become more efficient with how we use water, but we're going to be forced to go further. And going further is going to involve things like water recycling and stormwater capture and possibly even desalination.
Welcome to wet Singapore.
Yeah, nice to meet you. A great day for a walking tour, right? All the rain. Right, so I carry my umbrella in front of me, and you say, but women carry it further back, is that right?
Like that.
It's more elegant that way?
Yeah, so we can spin it.
Yeah, okay. How long have you lived in Singapore? Are you from Singapore?
My life.
Okay.
I was born here.
You're native, you're local.
I am.
Okay.
Yes, welcome to my hometown.
But Singapore also is a place where people from around the world come to. So there's Malay, Chinese, Indian, English. Are those the main ones?
Yeah, those are the main ones. Singapore has been a migrant city from the very beginning. And the river really, is where it all began. You had the Malays who were living here on the river. You had the Indian boatmen coming in to ply the river, taking people across the river before the bridges came up. And then the Chinese businessmen who were carrying the goods from the lighters to the go-downs. We're a very tiny space, right? We're only 718 square kilometers. So we invested in the brain services that we provide today.
And maybe that's an example of how the whole world should do it. It's something we got to be smart about our resources.
Since 1980, Singapore's population has nearly doubled and continues to grow. Today, Singapore is a global financial center with a population approaching 6 million people. As an island nation, Singapore has had to become very serious about solving water and energy challenges. With only a small amount of land, they don't have access to all of the water they need. But they have begun to solve this problem by using modern energy. Singapore is surrounded by ocean, and their water supply depends on removing salt from the oceans, or desalination, and also by reclamation, which means treating sewage and other used water to make it safe to drink. Both of these processes are necessary for Singapore, but require a large amount of modern energy.
Singapore is a small island. We have some 5.8 million people staying on this island. So you can imagine the stress that we have in terms of the water resources to meet that demand. When we look at Singapore, right, actually we have a lot of water in terms of rain. And the problem we have is we don't have the land to capture every drop of rain and to store it. So every drop of water that we get onto Singapore is very precious to us, but it's not enough to meet our needs. So that is why we have seawater desalination, which is weather resilient. Once we get all these water resources, it's important that we keep all this water within our water cycle. And water reclamation or water reuse is the way we do it.
In Singapore, the wastewater that flows down the drain and is flushed down the toilet is now being treated until it is completely safe to drink. This has sometimes been referred to as toilet to tap.
So the water demand in Singapore is expected to double in 2060, and new water is expected to account for some 55% of that water demand. And today, new water accounts for up to about 40%. So you can see that we are really expanding our new water capacity moving into the future. There is always this psychological barrier for people to reuse wastewater. So as part of to overcome these challenges, we recognize that we have to be very aggressive in terms of our public education. I think the question on energy intensity is relative. If you compare new water treatment to, say, conventional water treatment, it is maybe 4 times more energy intensive. But if you compare it to seawater desalination, which is another water source which is weather resilient, like new water is actually 4 times more energy efficient than seawater desalination. So it really depends on what you are comparing it to. I think we do receive a lot of interest from international community about how we implemented water reuse. It really comes from all over the world, like including the United States. The key interest from them is really how did we scale up the implementation into a nationwide campaign. It's really the public acceptance that is critical to any water reuse program.
The challenges around water are not the same everywhere in the world. For national security reasons, the nation of Israel cannot rely on its neighbors for a water supply. So Israel has turned to a combination of conservation, using less water, and advanced technologies to solve their water problems.
If you open the Bible, you will see that drought is part of our culture. It is mentioned also in the Bible that this area suffered time after time from drought, and this was the greatest fear of the people, to suffer from the drought. So when in the 90s we start to suffer from this severe drought, we knew that some severe action should be done.
Safety first, right?
Safety first.
Yeah, safety first.
Desalination after.
Yeah.
Okay. Yes.
So what are we walking by here? What is this building on
this
the right?
is the pre-treatment.
Pre-treatment, okay.
The first train, it is the second train. Each pre-treatment hosts 24 compartment of dual media filters.
You see
inside.
the size of the pipes is really incredible.
Most of the climate in Israel is desert. The rainfalls there is between 50 to 100 millimeters per year. So you don't have enough water, reservoir water. You cannot rely only on natural rainfalls. You need additional water resource. 2.5 meters.
2.5 meters, okay.
2.5 meters on the...
And that's for the intake pipe? Or
this
which
is
pipe?
we have 2 intake pipes like that.
Two intake to bring the water in from the sea?
Yes,
okay.
and 1 pipe of brine or concentrate in order to the effluent goes back to the sea.
That's the discharge. The sea is the same size?
Yes.
Okay.
In 1948, the population of Israel altogether was around 1 million people. But since then, we are 8 million people here. And the natural resources did not grow since then. So we had to find another solution. And this solution is seawater desalination.
It smells like the ocean right here.
Yes,
it smells like low tide or something at the beach.
So the water level here is about minus 6 meters. And from here, the water flow through a rotating screen, which remove all the rigid debris.
And those jellyfish are huge. They're like this big.
Yes.
I don't think I'd want to swim in that water right now. If we look at places like Israel, it's hard for them to get access to the water they need. So the way they solve it is with technology, money, and energy, and they invest all of it to get water from salty places like the ocean. That's one way to solve the water problem. So 7 pumps?
7 pumps, which discharge about 70,000 cubic meters per hour.
Seawater desalination, like any other water treatment technology, requires modern energy to produce water that is safe to drink. Electricity and natural gas both play a role in treating and filtering the water. In some parts of the world, desalination requires too much energy to be worthwhile. But countries in the Middle East view desalting the oceans as critical to their water supplies.
The water is already cleaner than what we saw at the intake.
The technology which is most common here in Israel and also in the world is the reverse osmosis technology using a special spiral wind membrane. Every 7 years, 100% of all the membrane should be replaced.
You can hear the pumps working right now. They're pushing water through the facility.
They're pushing water through to the Mycronic filters. The Mycronic filter is actually the last barrier. From this place on, the water is 100% clear.
Is this the end of the line?
Yes, this is the end of the line. Now we're going to drink water that 40 minutes ago were seawater.
Really? In the time we walked through this facility, we saw the water arrive, and now it's here and we're ready to drink it?
40 minutes past.
I think so, yeah, absolutely.
So, let's drink.
So this is the biggest seawater desalination plant in the world?
Yes.
And you and your team designed it?
Yes.
You must be very proud.
Very proud.
It's like your baby.
I hope I will have more
You want
more
babies?
babies.
Yeah, you're not done yet.
Not done yet.
Cheers.
I think deep in our heart, we all connected very much to nature. But at the same time, we were taught technology, energy, pumps, you name it. It's the only way to solve our problems. More and more people understand that there are limits to technology, and we need to go back, at least to create a new balance in the way we treat ourselves.
You can see the trees, the olive trees. This is about 500 years olives.
You know, I always say that the world today is facing two main issues talking about environment. One is the global demand for more water recycling, sewage water recycling. The other one is carbon footprint reduction. Using conventional one that's based on fossil energy, it will never end.
Using only the power of plants to purify wastewater without any electric pumps or fossil fuels is the mission of Israel's Ayala Water and Ecology. At this farm, sewage water flows through vegetation, where it is naturally cleaned and filtered, making it safe to drink without using a single ounce of fossil fuels.
It's all about changing the way of approaching the solution. This is actually our lab, and also this is a case study place where we show how the system operates and works.
I mean, I think to solve our energy problems is to use less energy. Today, people care more, but they don't know how. So this is a completely different approach to the watershed management. And it's all by natural means, not even 1 watt of energy. We're heading to a dead end, so we need to do something.
We definitely use water to produce our oil and gasoline for our cars. We have to actually extract oil and gas from underground, and to do that, today one of the techniques that's used is called hydraulic fracturing. Hydraulic fracturing, as the name might suggest, actually uses water to basically go down and break open the shale formation underground. We've actually reduced the carbon intensity of our electricity production here in the United States, and it's been actually fairly dramatic. But you use about anywhere from 2 to 9 million gallons of water per well to do that. So I would say hydraulic fracturing is a thirsty endeavor. We worry about things like wastewater spills nearby. That wastewater could be a liability to the environment and to human health. I mean, we just have to understand that the more water we need for our electricity production, the more vulnerable our electricity production is. I think that the industry is doing what they can to move away from freshwater sources for it. So they've been able to reuse some of the water on site. They've been able to use brackish water. But yes, it can be a thirsty endeavor. A lot of these decisions that we make today put in infrastructure that lasts for decades. So we really need to be thinking not just short term, but really like 50, 100 years down the line, because a lot of these power plants and infrastructure that we're going to put in place are going to be around for a really long time.
I'd like to see us think differently about water and energy moving forward by no longer taking these resources for granted. We trust the water that comes out of the tap is clean because of the energy we've put in to treat it and to disinfect it and to pump it. And we trust that when we turn the switch, the lights will come on, but we've kind of taken it for granted.
Part of the challenge in 21st century America is that we have to think about limits that we didn't previously have to think about. We could build a power plant in the 20th century anywhere we want and not worry about the water requirements. That's no longer true. In more and more places, water is becoming a critical factor in decisions about our energy system.
One of the issues is, what is going to be the hydro resource at any particular place as we get more global warming? There really are solutions that must be tailored to the regional circumstances. And that's within the United States, and that's between countries.
There is a clear link between water and energy. It's a cross-border, it is a resource. It is not just, luxury. It is a basic resource, and it has to be coordinated and managed together.
I think we know that there are solutions to all of the water challenges that we face. The truth is, we waste a huge amount of the water that we already spend a lot of energy and money collecting and treating and distributing, and we use it inefficiently. Let's think about sources of water that we've thought about as liabilities, like wastewater, desalination potentially, if we can get over the economic and energy hurdles. Capturing more stormwater is a new source of water. So if we do all those things, I think that leads us to a sustainable future for water.
Those who have energy need to reduce the environmental impact of their energy consumption. But those who don't have energy need energy. So we have to simultaneously solve the problem of energy access while reducing the impact of the billions of people who do have access. This dual conundrum is the grand challenge for humanity.
We all make choices with each appliance we switch on, the houses we buy, and how we live. Conservation and efficiency is one of the few solutions that any of us can help to implement. We can conserve today just by turning off a light to save water, or adjusting a thermostat to save water. Or we can use less water in order to save energy. Our modern energy system needs water, and our water system needs energy. Ultimately, energy and water are so intertwined that they have become nearly synonymous. Unfortunately, that means the risks of failure in one system can quickly cascade to the other. But water is only the beginning of the story of energy. Water and energy are the underpinnings of all the other systems in our modern society. Our food, transportation, wealth, cities, and even our security. By understanding these modern systems, we can begin to understand energy. Power Trip: The Story of Energy is available on Amazon Prime Video.